Hello everyone. We have been discussing about compaction. Already two sessions we have done. This is third session in compaction. We'll see further details about them. Okay, this is the syllabus part that we have to cover. In this definition of compaction, we have already covered principle of compaction. Also, I have told you mechanism of compaction, why the compaction curve goes up and then again comes down. Standard Proctor test I have talked. We'll see what is modified Proctor test. The effect of compaction on soil properties we'll see. Already we have done this. Field compaction control is going to be covered now. Compaction effort and method of compaction, lift thickness and number of passes. Proctor's needle and all will be studying in next class. Compacting equipment and their suitability will be covered in this session. So that is the planned program. This anyway, it is a plot of water content on x-axis, dry density on y-axis. You'll be getting a curve like that, typical curve of compaction, which goes up and then it drops down. The peak is recognized for finding out OMC, optimum moisture content, there on the water content axis, and then corresponding to peak you'll be having maximum dry density. Why it happens with all these figures, we have seen it number of times. Okay, here standard Proctor test, already we have seen that it will be having a base plate, a mold, approximately 1000 ml or 1000 cc capacity. To fill the soil, there is a collar on the top. Assembled equipment looks like that, and then this is the rammer, which is opened or lifted condition and then dropped condition. It will be having a 2.5 kg rammer inside, right? So if you want to calculate compactive energy in standard Proctor test, number of layers are 3. You have to fill the container or mold in 3 layers. The weight of the rammer is 25 newtons. It falls through 0.305. Number of blows per layer would be 25. The volume of the mold will be 950 cc to 1000 cc. So here it is written 945. So energy will be 3 times 0.305 into 25 into 25. So many Newton meter or 571.9. You can say joules per 945 ml. If you calculate for 1000 ml, it comes out to be 605.16 joules. So say you can say 600 joules is the energy used in standard Proctor test per 1000 ml per liter of soil. Sorry. Modified Proctor test, why it came into picture is, I can just see here, in early days compaction achieved in the field was relatively less. With improvement in knowledge and technology, higher compaction became a necessity in the field. Hence, modified compaction test became relevant. It was developed during World War II by the US Army Corps of Engineering to better represent the compaction required for airfield to support heavy aircraft. So that is the background or history. Now what is done in modified Proctor test, the same mold is used, but only thing is number of layers instead of 3, now it is 5, and then height of the rammer drop, instead of 0.305 meters it will be 0.45. So in feet wise it will be 1.5 feet, whereas the standard Proctor test has got 1 foot height fall. and weight of rammer is also increased from 25 to 45 newtons. The number of blows per layer are kept 25 itself. The volume of the mold remains the same, 950 ml to 1000 ml. Now energy used is calculated 5 layers. 0.45 into 45 is the drop, and multiplied by 25 number of blows per layer. Now if you calculate this, you'll be getting 2531.25 joules per 945, or it will be 2678.6 Newton meter or joules per 1000 ml. If you compare this with standard Proctor test, almost 4.5 times the standard Proctor test would be the energy used here, because it is around 600. So here it will be approximately 4.5 times more energy is used in modified Proctor test. Okay, field compaction control. Now, it is extremely important to understand the factors affecting compaction in the field and to estimate the correlation between laboratory and field compaction. Field compaction control depends upon, there are four factors. One, placement water content, because in the laboratory you have found OMC. So if they are using the same amount of water or less or more, it matters. So placement water content is an important point to be observed in field compaction. Now the type of the equipment. Now this you are going to study in detail. What is the type of roller or rammer to be used for different variety of soils? That is what we are going to study. So you should choose a proper equipment for proper soil. That is what is the idea here. Lift thickness. When the soil is laid for compaction, obviously if you lay it for large thickness like 1 meter or 2 meter and try to ram or try to compact, only the upper layer gets compacted. That's why you have to use lesser thickness layers. A recommended thickness is only 1.5 feet, that is around 45 centimeter, or sometimes it is recommended to go only for 30 centimeter thickness, and on upper layers will be asking only 15 centimeter thickness laid and then compacted. So number of passes based on soil type and degree of compaction. So when you run this, it is not just once you have to run it. You have to correlate between the achieved compaction and then number of times it has gone. Maybe for a particular soil, this has to go for maybe around 10 times. So 10 passes. If that is the thing, then you have to ask the driver to go for 10 passes only. If you reduce the number of passes, the amount of compaction that has been achieved by the compacted soil will be less. It may not be satisfying the requirement, right? So laboratory laboratory results have to be correlated with the number of things that are there on the field. That is what is field compaction control means. You have placement water content, the type of equipment, thickness of the layer or lift thickness, and the number of passes of a particular roller. Okay. Okay, now here, what is placement water content? It is the water content at which the ground is compacted in the field. It is desirable to compact at or close to optimum moisture content to achieve achieved in the laboratory, so as to increase the efficiency of the compaction. This is obvious because we have tested for that purpose only, to find out what is the best moisture content. Obviously it is recommended to use the same, but however in certain jobs the compaction is done at lower than or higher than OMC by about just 1 or 2%, depending upon the desired function as detailed in the table. So on the field, sometimes it will be made less or more, right? Why so? It is described here. Dry side in the sense 1 or 2% less than the OMC. Wet side means it will be slightly more than the OMC. So if I have to write here, the water content here will be OMC minus 1 or 1.5%. Here it will be OMC plus. Okay, I think you can understand this. OMC plus 1 or 2%. So if I write 2 here, so it will be like that. Okay. Now what are the conditions where lesser percentage is used? You can read it. Highway embankment compacted, dry of compaction, dry of optimum moisture content to achieve high strength. So because we have to use the high strength, so to get higher strength in highway embankment, slightly lesser water content is used so that low volume compressibility and good resistance to deformation is achieved. Okay. One more thing is high earth dams. Earthen dams, if you are constructing for a very high height, so earthen dams compacted at 1 or 2.5% less than OMC to reduce the pore water pressure development, because when the water flows, right, when the dam is holding water, it gets saturated, right? So better you keep the water content bit less so that the pore water pressure is slightly less. Next is wet side. Which are the cases? Cohesive subgrades under pavements compacted wet of optimum to eliminate swelling and swelling pressure upon submergence. Subgrade is nothing but a section for a road section, pavement section. Now that subgrade has to be compacted with little more of water, because if the roads get submerged in water, it should not bulge out. So in the beginning only you give it little more of water so that it is at particular volume only, right? So when there is a submergence, it should not bulge out and then give cracks and then fail. Next is impervious core of the earthen dam. So when you study earthen dam, obviously earthen dam will be having an embankment, something like that. So here there will be a small portion inside which will be for which it will be used a clayey soil or impervious soil, so that when the water stands on one side, even if it penetrates into this soil, it should not penetrate into this, or the uh, saturation line will be directly falling down. So this particular layer, which is known as core, right? So impervious core of earthen dam is compacted on wet side to achieve low permeability, greater safety against cracking due to different settlements. So whenever water comes, if there is a saturation, what happens is hardly there will be any bulging action, right? Already it is possessing more of water or sufficient amount of water. Because of the water that comes, standing water comes inside, it will not be bulging out or giving cracks. So that is the reason it will be compacted wet of OMC. Okay, that is placement water content. Next is degree of compaction. Now here, how the degree of compaction is measured is through RC, that is relative compaction or degree of compaction it is called. Now what it is simply gamma d of the field achieved. This is gamma d achieved, means when you lay the layer of soil, number of layers are done, and then ramming is done, and then afterwards to test how much is the ramming is done or quality of compaction done, what is done is a core is taken and then dry density is found, right? So that is the uh, idea behind finding out dry density. Now if this dry density which is found from the field, right, so this is what it is, dry density from the field. Now gamma d maximum from the laboratory. So in the laboratory you have already done a test on the same soil and then you have got this. So you have found OMC as well as maximum MTD. So this is from there. This is from the laboratory, this is from the field. So now if you find that it is equal to gamma d maximum, that is 100%, then there is no problem. But if it is less, then how much less can be permitted, or what should be the degree of compaction to be achieved? That is what is the point of discussion. Now correlation between relative compaction and relative density, you know ID, relative density ID is a function of White's ratio. If you know that E maximum minus E minimum divided by E maximum minus E minimum, in the numerator you have E max minus E natural, right? So that ratio ID multiplied by zero point 0.2 plus 80 gives you an idea about how much should be a relative compaction. Now typical value of relative compaction should be, it should be greater than 95%, right? In the contractor commitment it will be mentioned, it will be plus or minus 1 or 2%, right? Maybe if we say 2%, fine. If it is achieved 93%, fine. But if it is becoming less than 93%, means gamma in the field is slightly less than the gamma to be achieved as per the laboratory, then the contract has to uh, make some more passes of the roller or redo the work. So as per the requirement on the field, the action has to be taken. Okay. Now types of field compaction equipment. We have so many of them. Smooth wheeled steel rollers, pneumatic tired rollers, sheep's foot rollers, impact rollers, vibrating rollers, hand operated vibrating plate, and rammer compactors. Apart from this, you got two more types of compaction, which is called dynamic compaction and flotation. All those things are covered in detail in the next slides. Okay, here one by one I have shown smooth wheeled steel drum rollers. You might have seen all these kind of things, right? The capacity will be of the order of 20 kilonewtons to 200 kilonewtons depending upon the kind of work that you are going to do. It is self-propelled, there will be an engine and then it will be pushed, or sometimes it will be towed also, right? Suitable for well-graded sand, gravel, silt of low plasticity, unsuitable for uniform sand, silty sand and soft clay. So soft clay you will not be using smooth rollers. It is slightly coarse grained soils only it is suitable, and then not for uniform sand. So that is what is suitability of the equipment as far as smooth wheeled steel drum rollers are concerned. Now sometimes pneumatic rollers, so these are nothing but tires only, but the tires will not be having any uh, studs there, it will be a smooth one. So the purpose is to have a kneading action on the soil laid. So we'll read, usually two axles carrying a rubber tired wheels full of width of the track. So you can just see there are three of them, one at the center and two at the side, but almost full width. And then there will be three or four at the back side also. So there are two axles which will be having rollers, tire rollers, right? Dead load, which will be because of the water, is added to give a weight of 100 to 400 kilonewtons. You can just see here a tank, right? So this tank is, when it is filled, obviously the weight will be more. So when you don't want the water can be removed, so that weight will be less for the engine to move. Now when the water is added, it is in the range of 100 to 400 kilonewton. Now this kind of roller is suitable for most coarse and also fine soils. It is unsuitable for very soft clays and highly variable soils. Okay, next, sheep foot rollers. Now you can just see here the studs which are projecting out, they are of the type that it is sheep foot, that's why it is called sheep foot rollers, right? It is generally self-propelled. Hardly you find one which will be towed, but rarely that kind of thing will be happening. Nowadays all the equipments are self-propelled only. Earlier the roller used to be separate, and then it used to be towed by a tractor or somebody else. Now drum fitted with projecting club shaped feet to provide kneading action. So this gives you a kneading action on the soil that it runs, right? Now weight will be of the order of 50 to 80 kilonewton and suitable for fine grained soils, sand and gravel with considerable fines. So here obviously it is a kneading action, because of that it is a fine grained soil which is there. Even if it is for uh, gravelly soils, but it should have a lot of fines, means wherever there is a clay content or silt content more, then only sheep foot rollers is advised or used. Okay, impact roller, compaction by static pressure combined with impact of pentagonal rollers. Now you can just see that when it is pulled, suddenly this drops down here, so that gives you an impact. Because of that there will be a compaction. Obviously this axle will be having a play, so that whenever it is pulled up to a particular level, suddenly this drops on its own weight, right? Again it will be moved further, so like that continuously. When it falls, it will be free fall, and then it will be putting an impact load. Higher impact energy breaks the soil lumps and provides kneading action on the soil. Okay, next, vibrating drum. Roller drum fitted with vibratory motion levels and smoothens ruts. Nowadays you find whatever you find on the field, generally it will be having vibrations. The vibrations will not be seen by naked eye, because the frequency will be quite large, right? Because of that uh, here it looks like a plain smooth field rollers only, but it will be having an action of vibration, right? So vibration will be compacting the soil in a faster manner compared to static rollers. Then if the surface is small, or you are not able to reach by big equipments, in such cases it has to be compacted by plate and rammer compactor. It is used for backfilling trenches, smaller constructions, and less accessible locations. So when you are not able to do it with this kind of thing, it is recommended that you have to do it by plate and rammer compaction. Okay, suitability of the compacting equipment. Here I have listed different types of soils and then different types of rammers. So suitable, not suitable, all this is listed here. Whatever individual equipment we have done, the same thing has been put in the form of table. You can just go through. Okay, how does a contractor modify the compaction in the field? If this is the question, obviously what he can do is adjust the water content. If it is more than the OMC, it has to be less. If the water is added less than the OMC, it has to be added. Means adjust the water content so that you will get good compaction. Now if the achieved density is less, then he has to go for more passes of the equipment. Even then, if it is not happening, then you have to go for thinner lifts. As I have told you, maybe 30 centimeter is recommended, but if it is not getting achieved, then he has to go for lesser thickness so that more of energy is given for lesser amount of soil. Bigger rollers, the roller weights have to be slightly larger so that compaction effort will be more. Right compactor for suitable soil. Right, for different types of soils you got different types of compactor. If he is not using proper compactor, then also the soil will not be getting compacted. So this is how contractor can modify compaction in the field. Water content, more passes, thinner lifts, bigger rollers, and then right or proper compactor to be used. Okay, this is one more type of compaction. As I told you, dynamic compaction it is called, right? Used to compact both cohesive and cohesionless soils. A crane is used to lift a concrete or steel block weighing up to 500 kilonewton to a height of around 40 to 50 meters. Imagine 40 to 50 meter, 500 kilonewtons, and then it is dropped suddenly. From this height, the weight is allowed to freely fall on the ground. Right? The process is repeated over the area. Soil at surface is disturbed. It is then refilled and leveled. Right? So in the beginning, you have to fill the soil and then compact it. Now depth of compaction is up to around 12 meters. So this kind of soil, this kind of action will be able to compact the soil of the order of 12 meters. The method is quick and produces uniform settlement. So only idea here is overlapping imprints ensure uniform compaction. So here there is no overlap, because of that it is just like that. You have to overlap, means the next fall should be slightly over top of the earlier fall. Here there is a gap. This shouldn't happen actually, right? So that when there is a overlap, the uniform compaction will be happening. No loose pockets will be left. Okay, this is what is called as a dynamic compaction. This is a kind of ground improvement technique, it is called. Okay, the last one, vibroflotation it is called. Here it is used for compacting granular soils in the field. Consists of cylindrical tube, eccentric weight and water jet. I can just see it's loose sand recommended in that. Then there is a jet, right? Vibrofloat is sunk into the ground, and vibratory motion develops an enlarged hole. So there is a vibratory action as well as there is a jet. Hole is backfilled with suitable granular material applicable up to about 30 meters. Spacing of hyperflotation depends on initial density and desired density. Usually 2 meter spacing can enhance relative density up to 70%, means spacing between the holes. So once it is put into a hole, vibration as well as jet is used, and then extra material that is to be put will be put so that only the water comes out, and it gets rammed and densified. So obviously it is for loose sand, it gets compacted into a dense sand. It is said that if you use the spacing as 2 meters, then the density can be achieved up to 70%. Relative density can be up to 70%. ID can be equal to 0.7 or 70%. So with this, we'll stop. Thank you.